And in fact, different cultures will divide the scale in different ways with different kinds of consonant intervals. But these fundamental simple whole number ratios appear to be universal. And again, that is connected to the way the ear and the brain want to hear those simple whole numbers and call that a musical interval. So that leads me up to the last topic I want to touch briefly on, which is mathematically minded in the audience, is how do we make a scale? Now we've seen the intervals, the octave, the perfect fifth, the perfect fourth. And so we can build a scale up out of those. And in fact, the Pythagoreans built all of their scales entirely on these intervals and no others. So they built all their scales by fifths and octaves. So in order to come to another pitch, they would multiply or divide by 3 halves, that ratio 3 to 2, or they multiply or divide by 2, the ratio 2 to 1 for the octave. And so all of their adjacent notes were related either by a ratio of 9 to 8 in the frequency, or a ratio of 256 to 243. I told you, the Pythagoreans love their numbers. So if we have all of the different frequencies, so if we make a C scale, so we start with our lowest frequency, we call that 1. And then the D, the next pitch up, is in a ratio of 9 to 8 with the C, and we get there by multiplying by 3 halves twice and dividing by 2. And we can go all the way up the scale here. We get the perfect fourth and the perfect fifth, and all the way finally up to the octave. So simply by using ratios of 3 to 2 or 2 to 1, the Pythagoreans built up their scale. And it was based on the perfect fifth and the octave and the perfect fourth. This gives you a perfectly respectable and usable scale, but it has a problem. And the problem is that, suppose you start at C, at very low C, 32 hertz, and you go up by fifths. Okay, you go from C to G to D to A and so forth, and these are the frequencies. And so you end up, after you've gone up this high, you end up with what we would call a B sharp, and that's 4,152 hertz. You've just been doubling. If you start on the same note, but you go up now by octaves, multiplied by 2, you go up, so from C to C to C to C, you come up to what you would call C, and it's not the same frequency as that B sharp. Now, those of you who play the piano, you know that on the piano, B sharp and C are the same note. The note that is above B natural, which would be B sharp, is C. But if you start at C and arrive at that note by 2 different routes, you don't get the same pitch. And these two are very noticeably different. It doesn't take a trained ear to hear the difference. And so and that's a simple matter of mathematics, that if 3 halves to the 12th power is not equal to 2 to the 7th power. So you're never going to get this to close. And this discrepancy is referred to as the Pythagorean comma. And it's an interval that comes because when you go up by fifths and you go up by octaves, you don't end up with the same note. So if you want to make a scale that you are going to end up with the same note, you have to do some adjusting. And that's the practice that's known as tempering, or adjusting the scale. And so how are we going to do that? Well, the ear demands the pure octave. The octave is really the most fundamental relationship, that 2 to 1 frequency. So we need to keep that. So we have to adjust everything else to get rid of this Pythagorean comma, but keep the octaves pure. And there's different ways of doing that. So here's the Pythagorean. And we see, so if we start here at C, and we go up to C at twice that frequency, we keep our fifths pure, and we allow the other notes, we adjust the other notes to get rid of that comma. So the Pythagoreans kept the fifths pure and let the other pitches be a little adjusted. In the 16th, 17th centuries, there was the practice of mean tone temperaments, where they wanted to have the octaves pure, but they also wanted to have the thirds to be pleasing and consonant, our pretty major third. So they would allow the fifth and the fourths to be adjustable. So they would change the pitches of the fifth and fourth notes on the scale, but in order to keep those intervals of the third nice. The modern practice is what's called equal temperament, where you keep the octave, and you adjust all of the other notes so that they have the same interval between every two successive notes, every two successive semitones. And so the interval between successive notes, the frequency interval between successive notes is the 12th root of 2, or 1.0595. So the frequency of C sharp is 1.0595 times the frequency of C. The frequency of D is that same multiple of the frequency of C sharp, and so forth. So you've taken that Pythagorean comma and you just spread it equally over all of the pitches. So all of the pitches in equal temperament are equally out of tune, or equally in tune, depending on how you look at it. And it's simply a compromise that you have to make in order to have the different keys sound the same. I mean, on a piano, you can play a piece in C, and then you can play the same piece in C sharp, and then you can play it in D, and it will sound the same. I mean, the pitch will go up, but you won't perceive any difference in the intervals between the notes, the relationships of notes one to each other. If you have, for example, a harpsichord or a piano, well, nobody does this for the piano, tuned in a mean tone temperament, you play in C, you play in C sharp, and it will sound very different. And notes that work in nice ratios to each other in C won't be in nice ratios to each other in C sharp. So you don't have the freedom to modulate from key to key the way you do in an equal temperament instrument. And that's why equal temperament has become the standard now for tuning. It's because it allows you to play in any key you like, and it will always sound the same as it did in the other key. But different, even in Western music, at different times, people use different tunings. And so if you listen to, and composers who use these tunings took advantage of them. If they wanted something to sound nice and pleasing and happy music, they would use it in a key in which these intervals sounded pleasing. If they wanted them to express emotional distress and unhappiness and rage and whatnot, they would then modulate into a key in which these intervals now didn't sound right. They weren't in the same ratios. And so you could actually use that in an expressive sense. The practice of modifying instruments to make them more useful, better sound, or whatever, like retuning the piano, for that matter, developing the piano, following after the harpsichord, is an ongoing process that still continues to today. Here's an example of a flute. It's like an ordinary modern flute, but the holes, instead of being round, are square. And if you think about the details of the pressure distributions within the air column, you can see, yes, that would make a difference. And people who play the flute can hear the difference. It's subtle. It's not a dramatic difference, but it is there. And this hasn't caught on too much. This is made by a flute maker in Asheville, North Carolina, and he's sold a number of them, but hasn't certainly taken the world by storm. Dizzy Gillespie modified his instrument. He did it accidentally. I think he sat on it. And, but he said afterwards that he liked the sound better in the accidentally modified instrument than in the original instrument. And so thereafter, when he had a new trumpet made, he had it made like that because he liked the sound. And again, it's subtle, but the pressure distribution is going to change if you put a bend in that tube. And so you get a slightly different sound, one that he found to be more pleasing. And new instruments are still being made. New instruments that hadn't been seen before. What we think of as now the standard flute, the usual flute, was really a complete reworking of the flutes that existed in the mid-19th century by Theobald Böhm. And so he completely reworked it based on acoustic principles and made it, in fact, much easier to play, a much easier combination of keys without having to move your fingers around on the flute. The saxophone is, again, an instrument that was invented in the 19th century. It didn't exist before, by Adolphe Sax, hence the saxophone. And it has a very logical system of keys. It's actually a relatively easy instrument to play from that point of view. So new instruments continue to be made, and some of them become part of our ordinary concert and other kinds of music genre, like these two instruments. Other instruments have not yet quite gotten there yet. And so I want to show you a few really new instruments that have been made by students in my class. One of the assignments in the class that I teach is each student must make a stringed instrument and a wind instrument out of whatever they can find lying around their dorm room. And then the last day of class, we have a concert in which the students play their compositions for ensembles of these instruments. And it's interesting. Let me show you a few examples. This is the Frito-Lay men's bass. It's made out of the Frito box. That's the spoonsichord. It's a harpsichord, except instead of strings, it has spoons. And that one actually, as you can see, it broke on the way to class. So I think that one probably doesn't have a long future. This is the Sledola da Gamba, made out of a plastic sled and a push broom. And if you go to my website, you can hear it and also the song that the student wrote to go with it. This is the Skator, made out of a skateboard. And the student really wanted to be able to ride it into class, flip it over and play, but the bridge got in the way, so that didn't happen. And then that's the Huangzhou. It's made out of a bucket and a plant hanger and some other odds and ends. And if you go to my website, you can hear a duet between the Sledola, the Gamba, and the Huangzhou.
Was the 2x6 channel considered in here?
It would come into this category, but it was not made by the students. Here's some more. The Scythery-Doo. That was made out of a Halloween decoration, which was a scythe, a Grim Reaper scythe, a soda bottle, a Dixie cup, and a lot of duct tape. And this thing had two notes. One of them was C sharp and the other one wasn't. And this young lady had to compose for this instrument that had two notes. And the composition that she produced, actually, the head of the composition division in the music department came to our concert, which he does every year. And he said that given what she was working with, she did a very good job. It sounded like Philip Glass by Hangover. But, that's what she could do. The bottle blow, of course, we get a lot of instruments that are based on blowing across the tops of bottles. He assured me that he was not responsible for emptying these bottles. As a freshman, it would have been illegal. Yes, we get a lot of plumbing pipe in instruments. This one it's a sort of a bugle, and it played in he played it in an arrangement of the Blue Danube Waltz, which was very good. Panpipes, of course, are a very good instrument for this, and in fact, when this young lady made her panpipe, she was a flute player. This instrument worked really well. She could play it quite beautifully. But she learned a real-world lesson in making this because she sat down and worked out all of the length that she needed for the appropriate pitches that she wanted. She figured out what scale she wanted to tune it to and all of that. Yeah. And so she went into the hardware store and said, "Please, Mr. Hardware Store Man, would you please cut me copper tubing in these lengths?" And he looked at her and said, "Young lady, I need that in inches." Of course, she worked it out in centimeters like a good physicist. Yes, this young lady didn't believe me when I told her about the cement flute. And so for her wind instrument, she was a trumpet player. She made a cornetto out of plaster of Paris and played the Rudolph the Red-Nosed Reindeer on it. It sounded quite wonderful, actually. So these new instruments are probably not coming to any concert hall near you anytime real soon. But who knows what new instruments will be developed in the future that will be somewhat more effective than some of these, and that may turn up in different kinds of music that we'll be listening to in the future. So with that, I will just leave you to thank a few people, my colleague, Professor Brent Wissick, and of course the students of the class. And Don Ayler is a professor of clarinet at Chapel Hill, and he's responsible for the clarinet spectrum I showed you. Michael Schultz is the principal oboist of the North Carolina Symphony. He kindly provided the oboe spectrum. Those of you who are interested in learning more about this subject, I have 3 things to recommend to you for a book that's aimed at the general public. Is called Measured Tones by an Australian physicist and musician. If you want the hardcore stuff, the real details with all the Bessel functions and all the wonderful mathematics, I recommend this book for you. And then to have a conversation with one of the great minds of the 19th century, I recommend to you Helmholtz is On the Sensation of Tone. It's available as a Dover paperback. And it was a work that all candidates for musical degrees were expected to study in the 19th century. And my colleagues in the music department actually wish that that were still true. But they find it a little hard to enforce that particular dictum. But if you're interested, I highly recommend that you take a look at that. It's a wonderful book. And so with that, I'll come to the close of a rather flying tour through musical acoustics, and I'd be happy to answer any questions that you might have.
So why is the frequency certain tones?
I'm sorry, why is that?
So why do we perceive certain pitches as pleasant and certain? Let's say.
Would you repeat this question?
The question is, why do we perceive certain pitches as being pleasant and other pitches not? And as far as we can tell, it has to do with the two pitches held together, that sounded together, if they have a lot of frequencies in common.
I mean, that's actually not what I'm asking.
Okay.
Because you're just showing how we what happens actually inside the brain biochemically.
We don't know. That's an open question. And I mean, people are working on the auditory pathway and how does that work. That's not understood at this point. The wonderful subject of research for neuroscientists at this point. Yes, sir.
You showed a series of 8 instruments,
Mm-hmm.
and you showed that vertical.
The vertical viola.
I'm guessing that was put on somebody's knee.
On the knee, that's right. Yes, it's played like, if you're familiar with the treble viola da gamba, it's played like that.
Do you know of any recordings? Right at the moment, I'm thinking of Mozart, whose father was a concert writer
Right.
for the in place. And even before Mozart was born, was getting a free education when his father was practicing. Before he was born, he was getting his lesson. He wrote one of the most moving and most beautiful duets for a viola and violin. It is picturing his father playing the violin, which was the concert master, and he being the good son playing the other one.
Right.
It is called
Anyway,
do you know of any recording on that vertical?
of that piece, I'm not
How does that
aware.
sound
Yeah.
if the Mozart?
Well, yeah, it would sound very different because Mozart, of course, was writing his piece knowing the acoustic characteristics of the viola. And so I'm not aware of any such recording with the new vertical viola that I'm not aware. I don't think one exists. I certainly don't know of one. But if someone were to play the vertical viola in that piece, the balance between the two instruments now would be very different. It would not be what Mozart had been thinking about. Now, it might be very pleasing, but it would not be the same. Because Mozart knew what the viola sounded like, and he knew how to use it most effectively to accomplish his musical ideas.
The name that wasn't coming to me. It's Concerto Concertante.
Yeah, so I'm not aware of anyone having made a recording of that piece with the vertical viola, but it would be a very interesting experiment to try. Yes?
The Norwegian Hardanger fiddle has double strings and a very different sound. It sounds something like geese honking, passing over in sudden flight. How does that happen?
Well, I mean, the double string, of course, there are a number of instruments with double strings, and the two are not tuned the same.
Yes.
And so so you get those combinations of sounds, the different pitches depending on the frequencies of the tuning. The honking is mostly because the Hardanger fiddle is smaller than it should be in order to amplify those lower frequencies more effectively. So it's more like a viola in that sense, that it's undersized for its pitches, and so you tend to get more of the higher frequencies, which gives it that sort of more of an edge sound to it.
That's reassuring because an uncle played one of those when he was intoxicated. And I was completely sure about the physics of it.
Yeah, well, the skill of the player has something to do with it. That's something I haven't factored into this.
when you play the, say, a C recorder,
Mhm.
as you said, as you release certain holes, the pitch goes up. But if you want to play an accidental, you have a hole and then some cover.
Got cross fingerings, yeah. And that's because the actual distribution of the pressure, high and low pressure, is somewhat more complicated than I was giving you sort of the first simple version, and then once you start doing cross fingerings, the pressure distribution gets a little more complicated, such that you can bring out frequencies, you can have resonant frequencies that aren't simply as if you had shortened the tube. And the size of the holes matters too. And so how big they are, the diameter of the hole relative to the diameter of the tube will make a difference in what the frequency is when you open the hole. So I've given you the simple versions, but the details are more complicated, and that's where those cross fingers come. Yeah.
Can you explain the phenomenon of on a violin, you can play these super harmonics
Yes.
by on the very low strings by just pushing it.
What you're doing is if you, let me go back to find the right, slide here. Okay, what you're doing is, make it big. Okay, okay, the question is what the phenomenon of harmonics on a violin, where you get these on a low string, you can make a very high pitch by just gently touching the string in the right position. What you're doing is if you touch the string in the middle, right in the center, this lowest frequency vibration no longer can happen because your finger is keeping that from happening. So now the lowest frequency vibration is the red one, which is an octave higher. So the pitch you hear is the octave higher, and it has that sort of thin and insubstantial sound because any of these frequencies with a maximum vibration in the middle will be suppressed. So you'll get only the second, the fourth, the sixth. So it's a much thinner and more ethereal kind of sound. And of course you can do that. You can do that not just in the middle, but if you put your finger here, you're going to suppress both the first and the second, but not the third. And so now you're going to get the octave and a fifth up above. And of course, there's two places you can do that. You can put your finger in two different places and get the same harmonic. Oh yeah, try it. It's harder on a violin because you don't have as much string to work with. Cello, it's easy. Guitar, it's not so hard.
I have a question regarding that, because I play the flute, and my flute instructor always told me, in order to get the full tone, you produce the overtone with the same fingering. So you practice the overtone, and then you shift back to playing the actual note you're trying to get. But what is that physics of that overtone?
Okay, it's a matter if we go.
The same kind of thing?
Yeah, it's the same kind of thing. That you're preferentially exciting that second vibration by exactly how you look. And the details of how you're setting that air column into vibration can enhance the second partial over the first partial, which is that
So
all
that's
octave
what
that
you're
you
doing, is
Yeah.
by playing that second.
Exactly.
You're enhancing
That's
the
right.
fundamental. So that's what my instructor told me.
Exactly, and so your instructor is teaching you how to excite the vibration, how to blow properly, so that you enhance that higher partial. So you can actually you can make that. In fact, you can play the second octave, without changing the fingering, as you say, by enhancing that second partial and suppressing the first partial. And it's all in the details of that very complicated air jet that you're producing to start the sound. Yeah.
I can visualize the wave thanks to oscilloscopes and so forth. How did the Greeks do this? How did they discover this? Is that too?
Well, they didn't really understand the waves, but they had their stretched strings, and they would change the length and look at the ratio. And so, in fact, we have our students do this. We take monochords, and they sit there and they rediscover all these things that Pythagoras discovered. Yeah, so they didn't understand the wave physics as far as we know, but they could look at the ratios of the string lengths. They would tighten them all the same and then just change the lengths.
What number system did they use for all these complicated ratios?
Well, it's all. I mean, of course, they didn't notate it the same way, but they understood 1, 2, 3, 4.
Yeah, of course.
So, and these are just ratios of small.
I know the Greeks didn't use Roman numerals. Trying to do it in Roman
Oh, yeah, writing it out would be very complex, but visualize, I mean, literally visualize, you see it on the string. So you can see, yeah, okay, that's twice as long as that. So having the physical object in front of you, I think, helped a lot.
Doing the Pythagorean temple.
Yeah, you just keep cutting down to 2/3 or halves, and those are pretty easy ratios to do. Those are the only ratios they used, so that made it doable with no tools, essentially, but just with the string sets.
Well, thank you very much.
Thank you very much.